Hello, with this video, we're going to be talking about rational functions for section 4.5. Before we get started, let's recap on a few things, especially when we're dealing with rational functions and domain comes to mind. So we need to kind of recap and think about domains and what domain means and how to find a domain. Remember, the domain that deals with the x values, and basically I previously mentioned, there were three cases where the domain will show like a red flag. When you see a fraction, when you see even roots, and then when you see even roots within the denominator. So kind of both together. So here's our fraction, here's the square root, and then here's a fraction with the square root. If you don't look at a function and you don't see any of these cases, then the answer is always going to be all real numbers. So for this one here, remember, a red flag means what's going to make this function undefined. Undefined means that you cannot have a zero in the denominator. So this is where the q is located in the denominator, and it is not zero. So for this one here, if we said x was equal to 5, for example, 5 minus 5 is equal to 0. So we have 3 divided by 0, which is undefined. So this is where we say that the domain for this function is you can tell me any number that you would like that's going to work for this function except for 5, because 5 is the only number that's not going to work and it's going to make this a function. So for same thing, but here inside the square root, you can't have any negatives. So once again, so long as the inside of this square root is a positive number, or a 0, we can take the square root of it. When it becomes a negative, then we run into what is called again a red flag. And down here for both, it cannot be 0 or it can't be a negative number. So that's why it's going to be greater than 0, greater equal to 0, and then cannot equal 0. So keep this in mind when working in this section. So for here, let's consider the domain of this rational function. So again, what's going to make this cause a red flag? Having a 0 on the bottom, correct? So if we set this denominator equal to 0 and solve, we notice that x is equal to 0. So 3 is the only point that's going to make this here, down here, 0, which makes the whole thing undefined. So here, this is how it's written. From negative infinity to 3, so all the numbers in between negative infinity and 3, with union 3 to positive infinity. Notice here I put these in parentheses. Parentheses mean we do not include 3. We go up to 3. You use any number up to 3, but do not use 3. Same thing with infinities. Because infinity is not a definite number, we can't include it. Now, if I put a bracket around it, brackets mean you include that number. That means you can take this number and put it in here, and it's going to work. So because we put parentheses around, we can't use 3. So any number from negative infinity to 3, and then 3 is a positive infinity, will work for this function, and it's going to make it true, or make it, you can find an answer for it. 3 is the only one that's not going to work. So just looking at a couple of examples, again, remember, always set the bottom ones equal to 0. So if it's just an x, that means that's going to be the domain. So from negative infinity to 0, and then 0 to positive infinity is going to be considered to be the domain for this one. 0 is the only one that's not going to work for this one. The same answers for this one. If you set this equal to 0, again, 0 is the only one that's going to make this a red flag. Now here, if you're giving the x squared plus x minus 2, you know you have to factor it to figure out what the zeros is going to be, like the same thing in our previous chapter. Notice again in all these examples, I don't necessarily need anything to do with the numerator. So you can just kind of ignore the numerator because we don't really need anything to do with that. It's just the denominators. When we're talking about domain, just focus on the denominator. So this factors to this. So this 0 is going to be negative 2, and this 0 is going to be 1. So we can go from negative infinity, because we always start from the smallest number. Smallest number has to be a negative infinity, to negative 2. That's our first one. Then we go from 2 to 1, so from 2 to 1, and then from 1 to positive infinity. If you chose a number in between any part from here, any part in between here, and any part in here, this problem here is going to be considered to be a function, which is going to be great. But you cannot use -2 because -2 plus 2 is 0. 0 times anything is 0. 0 on the bottom, red flag. We don't want that. And then 1, if you put 1 over here, 1 minus 1 is 0. Again, 1. The 0 here times this, whatever this is going to still be 0, which makes this whole thing undefined. So basically here, again, you're just taking whatever the x is and set it equal to 0, and that causes us to figure out what our domain is going to be, what the number it cannot equal for the bottom. So here would be -1 and 2, and just make sure you kind of write it out like so. And the last one should be -1. Okay, so now that we had a good understanding of domain, now it's time to talk about vertical asymptotes. So here is the same problem we discussed on the very first example. We know the domain can be all the numbers except for 3. So 3, the vertical asymptote was considered to be at x equals 3. So anytime you figure out what the number cannot equal, the variable cannot equal, that's considered to be our vertical asymptote. So what does vertical asymptote mean? This is when graphs approach a kind of like an imaginary line. So we just can simplify it as a dashed line, but it's like an imaginary line from the left to the right, but it'll never touch it or intersect it. So here's my graph. When I create this graph, it's going along here and it's coming down. And notice it gets very close to the vertical asymptote, but never actually crosses it or actually touches it. And it continues on here. And then how does it continue? It jumps back up here and then continues on in this direction. So here, because this function here cannot equal 3, that's why these red graphs, right, you see here never will cross 3 because it can't equal 3. That's what's called a vertical asymptote. So here are some more examples. So here we need to figure out what the domain is going to be first in order to figure out what the vertical asymptote is. Basically, again, what this denominator cannot equal because we don't want it to cross it. We want to draw that an imaginary vertical line down the graph because we know this function here is not going to touch it when we draw the graph. So for here, once you factor x squared plus 2x minus 8 gets to these two, we notice we're going to have two vertical asymptotes. So one is going to be at -4, one is going to be at +2. So here's my -4. So we draw a dashed little line here. And then one is going to be at 2. So again, whatever the graph cannot equal, that's going to make it a red flag, that's when you draw your vertical asymptote straight up and down. Graph comes here, jumps back up here, makes this little curve here, then jumps back down here and continues on this way. So for certain ones, we're going to get into what is called holes. So here's the hole here. So let's kind of backtrack. So here's my function. The first thing we need to do is factor in an x. This is where we actually have to do a little bit to the numerator also. For here, we factor in x on the top, and then we factor this. This is called a difference of squares. So we have x plus 1, x minus 1. So on the bottoms here, being multiplied together. But notice here, this x here can cancel out with this x here. These x's here will cancel out. If you have something that will cancel out, that will actually create a hole. So think about what the denominator cannot equal. It cannot equal 0. It can't equal -1, and it can't equal +1. However, the one with the 0, because they cancel out, will consider to be a hole in the graph, like so. So here's my -1, here's my 1, and then when x is equal to 0, there's a hole at 4. So anytime something cancels out, this is where we're going to consider to be a missing part or a hole. So how do you find the hole? Again, whatever that part that's being canceled out. Now just pretend that if this was x minus 1, then if I have x minus 1 on top and x minus 1 on bottom, that means those cancel out, leaving us with a hole at 1. So anything that simplifies or cancels out from the top and the bottom will consider to be a potential hole. So you take that number, this case here is x equals 0. We're going to plug it back into the equation of the simplified equation here. So put a 0 here, put a 0 here, put a 0 here. That's what we did right here in red. Go ahead and calculate, and we notice that y is going to equal to 4. So when x is 0, y is 4. This creates the whole. So like back in my previous example, if I said again, if x minus 1 and I have x minus 1 here and those cancel, well, I'm actually going to put 1 here, put 1 here, and put 1 here. And then when x is equal to 1, whatever the number is over here will be the whole in the graph. So again, wholes only come from when we simplify and cross out if there's something from the numerator and the denominator only. Everything else is vertical asymptotes if it's nothing cancels out on the denominator. So here once again, I'm going to factor out an x. So I have x here. Don't make this mistake and start thinking you can cancel out this x with this x. This x is actually glued to this 2. It has to be separate, a multiplication sign on both being multiplied together. That this multiplies by this multiplies this. When it's separate or when it's a standalone, then you can cancel them out. Here, this is not a standalone x. It's with this -2. So don't make this mistake in thinking you can cancel these out and thinking there's going to be a whole at 0. It's not. So for this one here, we're going to set both of them equal to 0. So I set this equal to 0. Anything being multiplied together, you need to set equal to 0. So here we have x equals 0 for this one, and then set this equal to 0, this part equal to 0, and we have the square root of 5 plus or minus the square root of 5. So here are going to be my vertical asymptotes at 0, the square root of 5, and negative square root of 5. So this is going to be the negative square root of 5. Here's the asymptote at 0. I know you don't see the dashed line, but it's actually on the y-axis. And then here's the square root of 5 here. Next topic is going to be horizontal asymptotes. Now, horizontal asymptotes, we're going to be talking about the y, and what the horizontal asymptote for this one is y equals 0. So why is it y equals 0? So let's kind of backtrack to figure out why is going to be y equals 0. So notice for this graph here, y equals 0 is a dashed line going horizontally. And it's actually going to be on the x-axis because it's y equals 0. So here you see that this graph here gets really close to the x-axis, or this little the horizontal asymptote here, but never touches it also. Same thing here when it jumps up to here, it comes down and it gets really close but never touches it. So think about if you actually put in the number 100. Put in 100 here, do 1 minus 3. I'm sorry, 100 minus 3, which is 97. So put 1 over 97 in your calculator, you get this decimal. If you put 5,000 in for here, put in your calculator, we get this decimal. And notice here, as this gets bigger, going to infinity, 100, 5,000, 1 million, as it continues to increase, this number here gets closer and closer to 0. If you were to see how many zeros is here, so this here is actually 0. So as this gets bigger, the graph gets closer to 0, and will never equal 0, but it'll get really, really close to 0. So again, as it gets bigger, it gets close to 0, but never will cross the 0 and actually equal it. Same thing for here. If it gets smaller, if the numbers get smaller, again, it will get close to 0, but again, we'll never touch it. So for horizontal asymptote, we need to focus on the degree. If it has the same degree, what is the degree for this one? The degree for this polynomial on top, this time we actually focus on the numerator also. We need the numerator for this one. The degree on here is 2. The degree for this one is 2. If these are the same degree, pretty much all we're looking for is the coefficients in front. The coefficients in front will formulate the horizontal asymptote. So the answer for this one will be 3 over 2, or 1.5. So again, we don't have to make this real complicated. Notice that you see the degree for this one is 4. The degree of this one is 4. If these always are the same, we just say that the horizontal asymptote is going to be whatever the coefficients are in front. So in this case here, it's going to be y equals -7 over 11. So this case here, another case is, what if the degree on top is smaller than the degree on the bottom? Well, the horizontal asymptote will always be y equals 0. So we're focusing here. This is actually a degree of 1. This is a degree of 3. If this is always the case, smaller over the larger one, the horizontal asymptote will always equal 0. So again, we look at this one here for this example. We see that the degree of this one is 2. Degree of this one is 2. Nothing complicated about this. We're going to say that the horizontal asymptote is going to be at 2. So 2 over 1 equals 2. So y equals 2. For this one here, I want you to include all the asymptotes. So then we now to go look for the vertical asymptote by looking on the bottom. Set this equal to 0, and it's going to be the vertical asymptote at 0. So we have a vertical asymptote at x equals 0 because the denominator can't equal 0. And we have a horizontal asymptote at 2 because, again, these are the same. So 2 over 1 equals 2. So here we're going to talk about now oblique asymptotes. In this case here, what if the degree on top is actually larger than the degree on the bottom? We already know the vertical asymptote is going to be at 2 because, again, down here, x can't equal 2 because 2 minus 2 equals 0 on the bottom, red flag. However, if the degree on top is larger than the degree on the bottom, then what we have to do is we have to start off by doing long division. So anytime you see the degree on top larger than the degree on the bottom, we have to do our long division or synthetic division, whatever you're more comfortable with. For this one here, we do our long division, and we notice that the answer here is going to be 2x plus 1 with a remainder of 1. Now for oblique asymptotes, you don't have to worry about anything about the remainder. What we're focusing on is our answer up here, 2x plus 1. That's going to formulate our slanted asymptote. So this is where the slanted part comes in. So with y equals 2x plus 1, we draw a dashed little line. That's going to be our oblique or slanted asymptote. And then here's our vertical asymptote because, again, it cannot equal 0 at 2. So this is here. So we have our three cases. Vertical asymptote, again, you set the denominator equal to 0. You figure out how many vertical asymptotes you should have. And then draw a dashed line straight up and down. Horizontal asymptotes, there are a couple of you really focus on the degree of the numerator and the degree on the denominator. So if the degree of the numerator is the same, then we always going to know that just look at the front of the two coefficients in front, and that's going to be our horizontal asymptote. If the degree on top is smaller than the degree on the bottom, then the horizontal asymptote is always going to be y equals 0. And if the degree on top is bigger than the one on the bottom, then we have to do the long division first, get our answer to make our slanted asymptote. So let's put it all together. Let's find our zeros, find our vertical asymptotes, find our horizontal asymptotes, x-intercepts, y-intercepts, and then some other points to graph the line. So here is the graph that we need to do in all these 5 steps here. So if you want to kind of go ahead and start, you may pause the video and try to get as much of these as you can for learning aspects before I give out the solutions. So for here, we notice that when we factor this bottom part, it becomes 3x minus 2 and x plus 3. So we know we're going to have 2 vertical asymptotes. One is going to be at 2/3 and one is going to be at -3. And this is what the domain should look like. So negative infinity to 3, -3 to 2 over 3, and then 2 over 3 to infinity, when the domain cannot equal -3 and 2 over 3. So this is where our dashed little lines go. Now for horizontal asymptote, why is it the answer going to be y equals 0? Because if we look at the denominator, the numerator, what is the degree of this one? It's going to be 1. Understood 1 up here. What is the degree down here? 2. If the degree is smaller than the degree on the denominator, the answer for horizontal asymptote is always going to be y equals 0. So let's find the zeros now. So for the zeros here, so if we need to find the x-intercepts, we need to take the numerator of the problem and set it equal to 0. Because again, for x-intercept, the y in this case here, when you write your ordered pair, has to be 0. So what's going to make this whole problem here going to equal to 0? So if this top part is 0, it doesn't matter what's on the bottom. 0 divided by anything is the whole thing is 0, which creates our x-intercept. So we actually set the top one equal to 0 and solve. We get negative 3 over 2 comma 0 as our x-intercept. So for finding the x-intercept again, set the numerator equal to 0. If we need to figure out the y-intercept, we just plug the 0 in for all the x's. So every x you see, put a 0 in. We simplify and we get negative 1/2. So the y-intercept is going to be, in this case, 0, negative 1/2. So here are some other points. Remember, if you put this in your calculator, you can always hit second and table to get some, or graph to get some extra, to go to the table and get some extra points to graph them with. But here, to recap, here is our first vertical asymptote. Here's our second one, y equals 0. So we have another asymptote here, in this case here. And this is what creates the whole graph on this part. Here's another example. Again, you have to factor the denominator, which becomes to x plus 3, x minus 2 to get our domain. Find out our horizontal asymptote. In this case here, the horizontal asymptote is going to be y equals 1. Why is it y equals 1? Because we notice that this is exactly the same. It's understood 1 here, 1 here. So that means that the coefficients in front will create our y equals 1 for horizontal asymptote. So again, for the x-intercept, set the top one equal to 0. So we have two x-intercepts, one at -1 and one at 1. So make sure you make them into ordered pairs. Don't just say the answer is going to be -1 and 1. Make sure that for x and y intercepts, you have to create an ordered pair. Know where the 0 is located for each one. For the y-intercept, again, we're going to just place all the zeros in, and we get 1 over 6 for the x-intercept. And then for here, there are some times where for horizontal asymptotes, you might see the graph actually cross it. That's fine, and that can happen sometimes. It's just when vertical asymptotes, when it goes up and down, you'll never see the graph actually touch it. So graphs can cross horizontal asymptotes or obliques, which is okay, so there's no red flag for that, but they can never cross vertical asymptotes. So just keep that in mind also when you're doing these types of problems. So here's the application. So first we need to graph the function in the interval of 0 to 48, then find the temperature of T equals 0, 1, 2, 5, 12, and 24. So a person's temperature is T, is in Fahrenheit during the illness given by the function. So for here, the little t is considered to be time, and or in this case, hours. So if you look here, this is what the graph looks like. We put it in our calculator. So if we put for 0 hours, we notice that the person's temperature is fine, 98.6. However, after hour 1, it jumps to 100 degrees 0.6. After 2 hours, it goes to 100.2. And then 5 hours, 99.3. 12 hours, we're getting back to normal after 24 hours. So what is the horizontal asymptote in this case? Again, because the degree on top is smaller than the degree on the bottom, in this case here. Well, actually for this one here, need to incorporate this 98.6 in our original equation. So how did it jump from here to here? In order to add these two together, the rule for fractions is you have to have the same denominator. So the denominator for this one is t squared plus 1. So under here needs to be t squared plus 1. So this is actually considered to be the LCD. So on top and bottom, so you can put this underneath 1. So put a 1 underneath here. Multiply t squared plus 1 on top, t squared plus 1 on the bottom. and multiply them together, and this is where we distribute and get 98.6 t squared plus the 4t times this one here, and that comes on top, and then you don't have to write, you can write the bottom part just one time. So in this case here, we see that the degree is the same. So that's why we're, for this one to be the same, we have 98.6 over 1. So 98.6 over this 1 is actually going to be the horizontal asymptote. So what does this whole graph say? As the temperature goes on, as time, 1 hour, 5 hours, 12 hours, 24 hours, the temperature for this certain person returns back to normal at 98.6. What was the maximum temperature? We see at hour 1, the maximum temperature was going to be at 100 degrees 0.6. So here is going to be right here considered to be the maximum temperature. And to find this maximum temperature, again, it's kind of like what we was doing before, finding the vertex. And that creates, at 1, the temperature was 100.6 degrees Fahrenheit. So this concludes this section. If you have any questions or concerns, please let me know.